This video will illustrate some of the principles of solving first-order linear differential equations. A first-order linear differential equation can be written in the form y prime plus p of x times y equals q of x, where p of x is any function of x and q of x is another function of x. Now, the equation may not start this way. There may be a formula here that's multiplied by y prime, but we can write in this form if we just divide that out. So our strategy is going to be to find an integrating factor so that we can create a new equation where I multiply all the way across and I get, multiply by u on every term, so that I get u times y prime plus u times p of x times y equals u times r q of x. And the idea is, if we can choose u properly, this can be the perfect derivative of u of x times y of x. So that's our goal. This is always going to be possible if I solve for u as an integral, the exponential of an integral of our original p of x. So this is separable. If I take this equation, u prime over u equals p, then I can integrate both sides and I get the natural log of the absolute value of u is the integral of p of x. And so that's where I get my integration factor. U of x is e to whatever that integral was. We usually don't use the integral sign. That just reminds you need to calculate the integral. So once I have found my u, I can integrate this new equation. The derivative of u of x times y of x equals u of x times q of x. This tells me that my solution satisfies the equation u of x times y of x must be an integral of u of x q of x dx plus some constant of integration. And I would finish by dividing out that original function. Alright, so let's take a look at some examples. Our first example actually is an example of a separable equation. Just to remind you how that would work, I could rewrite this as y prime equals negative 3y. So y prime over y equals negative 3. If I integrate both sides, 1 over y dy equals the integral of negative 3 dx. And I can solve. I get the natural log of the absolute value of y is equal to negative 3x plus an integrating constant. And if I solve this, we found that this is always of the form some constant times e to the negative 3x. Alright, so that's our old way of solving it, and I want to illustrate the new way of solving it using the idea of a linear differential equation. So let's go back and let's identify what our function is. So here, my function p of x is the constant 3. So if I integrate that, I get 3x, and my integrating factor is e to the 3x. Alright, so what I'm going to do is I'm going to take my original equation, y prime plus 3, I'm going to leave a little space here, times y, and let's put our integrating factor in, e to the 3x is equal to 0. The purpose of the integrating factor is that this is actually the derivative of the integrating factor times y. So notice this is the product rule in reverse. The integrating factor is that missing piece that we need so that the left-hand side of my differential equation is the derivative of a product of y times our integrating factor. Alright, so now I've got my derivative on the left is equal to 0, and the only way that the derivative could equal 0 is if e to the 3x times y was a constant. And so if I solve for y, I get y equals a constant times e to the minus 3x. This is my general form. And I want you to compare that to our original form, y equals a e to the minus 3x. These are actually the same. Okay? So, solving a linear differential equation with an integrating factor is finding that missing piece to make this derivative on the formula on the left coming from a product rule. Alright, so I'm going to take something very similar to the previous example, and the only difference now is that instead of equals 0, this new formula equals x. And I want to see what that does to my problem. The other thing is I've added an initial condition, so we'll deal with that as well. Now, my equation is already in the form of a linear first-order differential equation. Again, I've identified this product that's multiplied the y as this constant function, and just as before, the integrating factor is e to the integral, or e to the 3x, of that function. Okay, now I'm going to again rewrite the equation, but this time there's a difference. I have a right-hand side. So let's put in the integrating factor e to the 3x, e to the 3x, e to the 3x on every part. And just as before, the left-hand side is in the form of a product rule. It's the derivative of our integrating factor, e to the 3x, times our unknown function we're finding, y, and that's equal to x e to the 3x. Okay. Now this is where we come into something different. Instead of being equal to 0, the derivative of something equals this formula. That means that e to the 3x times y has to be an antiderivative of x e to the 3x. And there's going to be an integration constant that comes out of that. Alright, so now I need to use maybe integration by parts. So let's see. If I do integration by parts, u equals x, v prime equals e to the 3x. So v is 1/3 e to the 3x. U prime is 1. And so this integral is uv, so 1/3 x e to the 3x minus, so uv minus v du. So I'm going to have an integral of 1/3 e to the 3x times 1 dx. Okay, so that gives me my final formula, 1/3 x e to the 3x minus 1/9 e to the 3x plus the integration constant. E to the 3x times y equals our formula on the right. And if I solve for y, by multiplying by e to the minus 3x, I get 1/3 x e to the 3x divided by e to the 3x cancels, minus 1/9 e to the 3x and e to the minus 3x cancel, but the constant does not, so c e to the minus 3x. So this is the general solution, so let's mark that. This is the general solution, and we have an initial condition that will let us decide which of all the c's I need to use. So y of 0 equals 3, so if x equals 0, y equals 3, that'll tell me that 3 equals, let's see, this is going to vanish, so minus 1/9 plus c times e to the 0, so that's plus c. And that tells me, if I solve for c, c is equal to 28 ninths. My specific solution is 1/3 x minus 1/9 plus 28 ninths e to the negative 3x. And this is the final solution that takes into account not only the differential equation, but also the initial condition. Okay, for our third example, I have a differential equation. This time I've changed my p of x. It's no longer x. I have a new problem. Let's just identify our integrating factor. P of x is cosine of x. So when I integrate p of x, I'll integrate the cosine. I'm looking for an antiderivative of cosine, and that's the sine function. And so my integrating factor is e to the integral, so e to the sine of x. I'm looking for, I'll take that function and I'll multiply throughout my differential equation. So I get, let's write down our new equation, y prime plus cosine of x, I'll leave a gap for my function, times y. Let's put in our extra piece. The integrating factor, e to the sine of x, e to the sine of x, and this is going to equal x times e sine of x. And now the left-hand side is the form of a product rule. It's the derivative of our integrating factor, e to the sine of x times y. And so this is our new differential equation. X e to the sine of x is equal to that derivative of a product. Now this is an example of a problem that can't be solved all the way out. Like I can't come up with a formula. But if I were to try to solve for y, let's see, I get e to the sine of x times y is equal to an antiderivative of x e to the sine of x dx, and there's going to be some unknown constant. And the problem is we don't have a way to find that antiderivative using algebra. Well, this is why the fundamental theorem of calculus was created. I can write this antiderivative as an integral. Oops, let's not use red here. I can write this as a definite integral from some starting point. I'm going to choose 0, but you could choose any convenient number. And now the value inside can't be x anymore, so let's call it, let's do z. Z e to the sine of z dz. So this actually is an antiderivative. That's what the fundamental theorem of calculus says. So plus c, and this is equal to e to the sine of x times y. And I can write down a formula now for my solution. I get e to the negative sine of x, because I divided it to the other side, integral from 0 to x of the formula z e to the sine of z dz plus a constant times that exponential. So c e to the negative sine of x. And although this doesn't look like it's a very convenient solution, it's well set up to be able to put into a computer and allow a computer to find a numerical value. And this is my general solution. Now if I had an initial condition, I didn't in this example, if I had an initial condition, I would want to pick this starting point to match the value of the initial condition, because then when I evaluated y at, say, x equals 0, this integral is 0, and so I don't have to worry about that term. So let me illustrate that. If I had y of 0 was 2, for example, then what that would say is my equation would be 2 equals e to the negative sine of 0, integral from 0 to 0, z sine of z, exponential sine of z dz. And this whole thing is 0 plus c e to the negative sine of 0. And sine of 0 is 0, e to the 0 is 1. And so I get c is equal to 2. And my solution would actually have been e to the negative sine of x, integral 0 to x, z sine of z. I did the same thing again. Let's see. E to the sine of z dz plus 2 e to the negative sine of x. And that would be how I would use my initial condition on a problem like this. If I had an initial condition that was not at 0, maybe it was at 1, I would have chosen 1 for my starting condition so that this initial value problem would have made the integral really easy. Alright, as I was looking through the web work, there's a hint I want to give you. And the hint is there's a formula x to the x. You want to think of that as the exponential base e of x natural log of x. So here the power x matches the x in front, and the base x corresponds to the natural log of x. That's similar to the argument that if I take b to the x, that's e to the x natural log of the base. So when you're doing your work, you may find it helpful to think about your exponential as e to the x log x rather than this weird formula that we don't know what to do with, x to the x. All right, well, good luck on those problems.